And now we're going to do something with those vector valued functions. That's really kind of the whole point. All right, so let's see how I want this. Okay, so we have given in number 3, r of t is equal to 3 tangent t I plus 4 secant t j plus 5 t k. We want to evaluate and make a determination of whether or not there's any domain restrictions. Now we could use GeoGebra for this to graph the curve, but you've kind of seen me fiddle around with that enough to know that if I try using the touch screen and do it that way, it's not gonna be pretty. So I'll take you through this one by hand, or as by hand as like we typically do in this class, which is to say with the support of a calculator. Right. So let me get my pencil. Let me get my cough drop. So get rid of the star. So we're asked to find r of 0. So r of 0, as a first part of the problem. So r of 0 would be equal to 3 tangent of 0 I plus 4 secant 0 j plus 5 times 0 k. Okay. You can feel free to skip steps when you do this on your own. It's not really necessary to show the actual substitution as it is to come up with the result. But tangent of 0, sine of 0 over cosine of 0, that's the result of 0. Right? So we're looking at 0 I plus, now 4 is going to get multiplied by the reciprocal of cosine of 0. Cosine of 0 is equal to 1. Reciprocal of that is also 1. So 4 times 1 j plus 0k. So the result here would be just 4j. All right. So that's all it was asking us to do, just to evaluate the function, right? The vector valued function. Now, there is more that we're going to do with this, obviously, but we're kind of going right back to algebra 1 or college algebra with this kind of new type of function. You got to kind of build it up right from the ground floor. Right, so that's what we're doing here. Right, so I'm going to evaluate again, this time with a pi over 2. So 3, and I'll do the substitution. 3 tan pi over 2 I plus 4 secant pi over 2 j plus 5 times pi over 2 k. All right. Now again, tangent is equal to sine over cosine. So tangent of pi over 2 would be sine of pi over 2, which is 1, over cosine of pi over 2, which is 0. So that part of it's going to be undefined. If one part of it is undefined, then the whole thing is undefined. As it turns out, multiple parts of this function are undefined, right? Because secant of pi over 2 is also undefined. The only part that actually ends up being defined would be the k component, but that doesn't matter for anything because once one part of it, like I said, is undefined, the whole thing is undefined. So undefined. All right, so the last component here, or last part of the problem, oversell it. 3 tangent 2 pi over 3 I plus 4 secant 2 pi over 3 j plus 5 times 2 pi over 3 result multiplied by k. So the result is going to be based off of whatever these compute out to be. All right, obviously. Let me just clean that up. All right, tangent of 2 pi over 3. All right, so that's sine of 2 pi over 3. All right, so that's radical 3 over 2 divided by cosine of 2 pi over 3, which is 1/2, negative 1/2. So we're looking at negative radical 3. Now, maybe you don't know that, and that's fine. Right? Sometimes you'll have to know your trig relationships, and sometimes you can get away without knowing them. So in this case, you just type in tangent 2 pi over 3. You get a funny decimal. All right, so what you do is you just take this expression and square it, because you figure that it's got to be the square root of something. All right, and so if it's a square root of something, then all you have to do is square it and you'll figure out what the radicand is. All right, but we don't want to lose sight of the fact that it is negative. All right, I didn't get rid of my actual power tool. All right, power tool, that's funny. So I have the 3 that was already there, multiplied by negative radical 3. That's all coefficient of I. Secant 2 pi over 3, that's the reciprocal of cosine of 2 pi over 3. Cosine 2 pi over 3 is negative 1/2. Reciprocal of that is negative 2. But again, let's say, maybe you don't know. All right. The benefit of the Desmos calculator, well, one of the many benefits of the Desmos calculator, once you get over the learning curve, that distinguishes it from a TI calculator, is it does have the reciprocal trig functions. I almost said TIG functions. That doesn't even make sense. Trig functions. So you don't have to worry about the workaround, which wouldn't be too crazy, of typing in 1 over cosine. So either way, you're going to get negative 2, which multiplied by the 4 is going to give you negative 8. So negative 8j. And then the last bit, there is no trig function, so it's just 10 pi over 3. And then it's just a matter of cleaning it up. Maybe you didn't write it the way I did the first time around, so there wasn't anything to clean up. But what I'm going to do is I'm going to just kind of clean it up on the fly. Benefit of digital ink. Yeah. Some of us are pencil paper people. Others have kind of just moved into the realm of digital ink and never looked back. Some of us are kind of like, hybrid's a pretty popular word these days, so I'll just use that. Kind of taking a hybrid approach of doing a little pencil paper here and there, a little bit of digital ink here and there. Basically digital ink, but then when it gets too complicated, pencil paper. Whatever works for you, but it's little things like that, just copy pasting and moving things around. That for me is the selling point, the big selling point on digital ink. All right. So that was the problem on page 41. Now, in terms of the computation, but in terms of answering the actual question, are there any domain restrictions? Oh yeah, because I got one of those values to give an undefined. The big question would be, are there any other? I kind of ended the sentence after saying any, which was weird. If you haven't gotten to the final conclusion that I might be kind of a weird person, you'll get there. Or at least I say weird things sometimes. I don't know why. I can't control what comes out of my mouth. I don't know. Anyway, so the undefined component, is that the only instance in which this function would be undefined? No, it would be undefined whenever cosine is equal to 0. All right, so I'm just going to make a little notation here. I'll write it in the form of a semi-complete sentence. This function is undefined whenever cosine, the argument is t, so I just want to make sure I didn't put a theta there. Cosine of t is equal to 0, right? And just to answer the question that might be on my mind, if I were in your position, is well, okay, why cosine of t? And that's because if I focus on just the two elements that could be undefined and just rewrite them based off of, simple trig, nothing too crazy, nothing too fancy. This is the same as saying sine t over cosine t. And this is the same as saying 1 over cosine of t. For the most part, with the exception of things like piecewise functions and things of that nature, you could also have like step functions and stuff like that, which is really just a special form of a piecewise model. You're really just looking, when you're talking about domain restrictions, you're looking for any value that'll make the function undefined, any value that'll make the function imaginary, and then you also have what we call a practical domain. So any value or values that don't fit the context of the situation. So if you're talking about, the height of an object off of the ground, like above the ground, I'll be very specific about that, the height of an object above the ground, then in that context, if 0 represents the height of the ground, then negative numbers wouldn't make sense. So things like that. All right, so this function is undefined whenever cosine of t is equal to 0. But if it were as simple as that, math wouldn't be as complicated as it is. We have to state under what circumstances cosine of t is equal to 0. That happens, so I can solve this, t equal to the inverse cosine of 0 would be any value of t that puts the unit circle really on the y-axis. So that's pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So odd values of pi over 2 in the positive direction, but also in the negative direction. Right? The even ones will put it on the x-axis. So if you have like 2 pi over 2, that's the same as pi. That's not a problem. It's only the ones on the y-axis because, again, in the unit circle, I just had a moment there where I can't remember. I know I made a bonus opportunity for somebody to remind me to make. I made it a bonus opportunity for somebody to remind me to make the second unit circle bonus available, and I feel like I didn't do that. So I gotta make sure I take care of that. Anyway, just note to self, I'll check on that. So any instance in which the x value of a coordinate is equal to 0, because x is the cosine value, that'll put you on the y-axis. So we're talking plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, but we don't want to write it like that. That would be pretty awful. Right? We want to write it really as a sequence of values, right? So what I would want, we're looking at odd numbers. So I want, well, at least odd coefficients of pi. So for odd number, you might remember this from Calc 2 when you were evaluating sequences. You double a value and either add or subtract 1 from it. So if I say that I have some value n, that could be any number from negative infinity to infinity. Double it, I'm guaranteeing that it's an even number. Add 1 to it, because the distance or displacement from an even number to an odd number is always 1 unit. I'm guaranteeing that I'm looking at an odd number. All right, I could also say 2n minus 1, because it's the same idea. All right, so what I would say is t would be equal to 2n plus 1. Right? That would be multiplied by pi over 2. Right? So I could write it in a couple of different ways, but the easiest way to write it would be to just pop this over a 2 and multiply it by a pi at the end. So now what I'd want to do is just guarantee that I'm accounting for all possible values of n, right? So that would just be, a simple statement. So semicolon, n goes from infinity, negative infinity to infinity, right? But only the integer values, right? I don't want decimal values because that'll account for values in between, like for example, 1, 2, 3, 4, whatever. Right? So what I would say is that n belongs to the set of integers. So that's that weird z. You might remember that weird z. And I'd never do such a hot job of it, so I really got to kind of zoom in. But it's a z that's got like that double diagonal. That represents a set of integers. That should be familiar to you. I don't know how often you had to write that, but you should have seen that before. Now, since this is a restriction, and you could verify this, you just pop in, all right, pop in a 0, what do you get? You get pi over 2. You pop in a -1, what do you get? You get negative pi over 2. You pop in a 5, you get 11 pi over 2. We're all good here, right? But the restriction would be that t can't be any of these values, right? So my restriction, if I want to just kind of tuck this in here and just kind of move this down, is that t is not going to be any of these values. All right. So there's actually, in terms of the, are there any domain restrictions? There's a little bit more than the question was really asking for here, because I mean, it was kind of implying a yes or no, but you know better. On a test, it could be, are there any domain restrictions? What are those restrictions? Only an analytic response will be accepted, so we want to be prepared for the worst and hope for the best, But it could also be, like the hoping for the best would be it's a multiple choice question, and it's like, which of the following is a restricted value for this vector valued function? That wouldn't be that bad. Although, if I'm in your position, I kind of want this question to be the kind of problem where I have to show all work, because maybe that means that one of the more challenging calculus-y type questions would be ones where you just pop an answer in a multiple choice question. That's all stuff to keep in mind. Right? But a lot of trig going on there. Pretty spicy stuff. If you're a little iffy on the notation, but definitely take your time and review that. All right. The moment you've all been waiting for, limits. All right. It actually shouldn't be that bad. So I was going to stop the video and record a new one, but I think I'm just going to keep going. So the limit of a vector value function works pretty much the same way as limits work in general, which is to say that you have different ways to find the limits depending on the different situations that you're presented with. All right. Sometimes you're looking at a question that asks you to find the limit as you're approaching infinity, as your parameter is approaching infinity. Sometimes it's approaching a constant. What do? Well, you just do it the same way you would do it if this were single variable, Calc 1 type limits. You're plugging in, or you're finding asymptotes and such. You're just doing it for multiple functions simultaneously, right? So when I take a look at number 1, it's just asking you to find the limit as t approaches 3. The first thing I'm looking for is to see if there's any restrictions on this function, right? On this vector value function. And it's very important that we reviewed what we just talked about, the material on the previous page, because that's happening behind the scenes when you tackle problems like this. It's the rationale that goes into the thought of saying, all right, so if I'm going to find the limit as t approaches 3 of this function, all I have to do is replace each t with a 3. Right? My license for being able to do that is because there are no restrictions to this function. Right? because I'm looking at it and I'm saying, well, not a trig function. There's no radicals in it. There's no fractions in it. So there's no way, and there's no context. So there's no way this function could be undefined, imaginary, and there's no contextual situation that would say, okay, well, I don't want to have negative numbers or anything like that. It's not a piecewise, so there's no gaps or jumps or anything along those lines. All right. So it really just ends up being a matter of saying, right, I'm going to take this value of t approaching 3, and I'm going to replace all my t's. That's not, so my t squared minus 3t plus 4i plus 4t plus 3j. And because this one is in I'm sorry, I keep saying multiple variables. I mean multiple dimensions. All right, because this one's in 2 dimensions, you could actually use Desmos and the parametric functions on there. But I don't think you need to, because it's just a matter of saying, all right, like I highlighted there already. I don't want to highlight too much. 3 squared minus 3 times 3 plus 4 I plus 4 times 3 plus 3 j. And then, clean it up. All right, so we got 4i and then we have, what is that, 15j? All right, so that would be my limit. Now, what that means is a different story altogether. Just because we do it the same way we would do it in Calc 1 doesn't mean that it has the same meaning as Calc 1, right? What we're looking at here, and I can actually just show you really quickly. I'm about to type in as if that's going to do anything. I can just X these out. Just pop it in as an ordered pair. I always run the risk of getting my Desmos and GeoGebra confused. So I already feel like I'm doing this wrong, but that's all right. Failure, the best teacher is. Get a little RFT in there. That feels right. Feels like something I need to do. And then we have 4t plus 3. Yeah. Well, it didn't give me an error, so I'm feeling pretty good about it. So I would just pop in, let's try it, R of 3. And okay, so that did nothing. Well, I got, plotted something. 4i plus 50. Oh, it plotted the right point. All right. That's great. It didn't plot the function at all. But that's, I think, because I gotta admit, when I don't know all there is to know, either I don't know how to do it or Desmos doesn't do it. It's possible that it's more likely that I don't know how to do it. But you can get your parametric function in there, and you can pop the value in, and it'll plot the point. Right? You could label it up if you want. It'll put the value there. So 415 is plotting it as a point, and then you can just kind of at least reference it. All right. The the issue that we run into here when we're talking about coordinates in space following particular values, we can kind of manufacture this using Desmos by using line segments and things like that. But really what's happening is you have a set of vectors like we talked about on the previous page that trace out a curve. All right. It's the vectors themselves that are approaching this limit. Right. So all of those vectors coming in from one side, coming in from the other, because this is 2 dimensions, those are approaching this vector. But it's not a matter of approaching the point along the curve. The vectors themselves are changing in terms of their orientation with respect to one another, right? So that's a little bit of a hand-waving explanation. I'll pull it up on GeoGebra later because I know that GeoGebra will do it right. It's just one of the few things that GeoGebra does better than Desmos, so we'll just kind of deal with it. But we could, like I said, we could come up with a line segment here. I'll do it later on GeoGebra. All right. So looking at number 2, you can see here, hopefully what I'm talking about, the idea that if you got radicals, you got trig functions. Now, the sine function's everywhere continuous. So I'm not worried about that. It's the radical that I'd be more concerned about. Right. So as long as that -2 doesn't cause a negative under the radical, then we're going to be okay. Right. So instead of writing this all out, what I'll do is, the shorthand notation, limit as t approaches -2, and then of r of t, instead of writing the whole thing again, just to substitute in, we'd be looking at, again, the idea that we're just replacing all of our variables with the constant, the limiting constant. Just bear in mind that you don't even start the process unless you have reason to think that you're going to get a result here. All right, that's defined. All right, so 4 plus 6, so 10 minus 1 is going to give you a 9. Under the radical is going to give you a 3. So 3i. 4 times -2 is -8, plus 3 is -5. Then for the sine function, -2 plus 1 is -1. -1 times pi over 2 is -pi over 2. So sine of -pi over 2 is equal to -1, so minus k. All right. So you can crunch the numbers in your head. You can use Desmos, GeoGebra when I show you a little bit more later on. But bottom line is these should be the, I want to call them gimmies, because they can be kind of challenging depending on the nature of the function, but they're not going to be the challenging problems in this unit. All right. I just got to check something real quick. All right. Because we had issues at my high school today. We had to go remote because of a positive test. I'm waiting on information as to whether or not I'm staying home tomorrow, going in. They said that they'll call teachers if they had contact with the students. So now every teacher in the district is waiting nervously to find out if they've been exposed. And so it's just terrible. All right. So the next one, given the vector valued function, t, then t squared plus 1. So that's a parabola. It's just a question. When you have a vector valued functions in two dimensions where the highest degree is a power of 2, so it's polynomial, but the highest degree is power of 2, it's going to be quadratic. It's just a question of, is it going to be an upwards and downwards parabola, or is it going to be a sideways parabola? In the end, it doesn't really matter for what we need to do. We're talking about continuity here. So in A, they're just simply asking us to find the limit. So limit as t approaches -3 of r of t is going to be -3. So I'm just popping it in. These are two continuous functions in and of themselves. A linear function and a quadratic functions are everywhere continuous. So that requires little to no work in order to rationalize, like the traditional definition of rationalize, not like the math one. So -3, then we're talking 10 Now, in part B, it kind of seems strange to ask what seems to be literally the same question again. But there is a purpose behind it. And unfortunately, I gotta say, and this is not, I'm trying not to get on a soapbox here, but in Calc 1, this is one of the topics that are most commonly skipped, or that, yeah, or is, I don't know. So when you're talking about continuity is talking about passing the continuity test, which is saying that the function exists at a point and that the limit exists at a point in such a way that it's equal to whatever, back to Calc 1, whatever the y value is at that location. All right. So I'll just go back here for a second, and I'll just jot down a quick Calc 1 example. All right. So in Calc 1, this is what a problem would look like. All right. And you'd know going in that it wasn't continuous based on what I'm about to draw. I just don't understand why horizontal and vertical easel. Those should be the defaults. Could also be perspective. I'm on an angle here. Anyway, so let's say I have this function, this arbitrary function, and there's a hole, and then another arbitrary function going the rest of the way. And then at this location that I'll call A, again, we have that hole there, but it's specifically at A. Let me just kind of trim it up a little bit. All right. So at A, there is no value. The function doesn't exist. Right. So if I were to say, and I'll call this function y equals f of x. All right, so this function, this y equation is a function of x. All right, so f of a does not exist. All right, but the limit as x approaches a of the function. So if you have some kind of point that's traveling along the curve, and that point is traveling from left to right. So you start on the leftmost part of the graph, and you travel as you get closer and closer to that A value coming in from the left. You'd be asking, what y value are you approaching? Well, there is a y value there, right? It does exist from the left. There is some sort of finite y value. Now, it's unknown to us, but there is some sort of finite y value that does exist. All right, now coming in from the right, that point traveling along to the left, again, it's approaching a location that has a finite y value, right? Something that we would be able to determine on the y-axis if it was given to us, any kind of scale, but it's not given to us. We do know that it's approaching the same location from the left and also from the right, all right? So I can say that this function, this limit does exist. Right, but because these two values, this one and whatever this ends up being, are not the same, the function is not continuous. Right, so f of a is not equal to the limit as x approaches a of f of x. I'm sorry, I wrote f of a, I meant f of x. So we would say that the limit, well, we already know that the limit exists. We would say that it is not continuous. Right? Let me just kind of shunt this down over here. So therefore, not continuous. U-O-U-S. All right. So that's one example of continuity, or at least an attempt to prove continuity. Now, looking at it, all right, well, it's not continuous. Why? Because it's not continuous. That's why. But when you're going after a proof on this, that's a little bit of a different story. You gotta do the work, right? And like I said before, unfortunately, this is the most commonly skipped topic, or one of them, in Calc 1, because it's like, all right, we don't have time for this. So just if you could draw the entire graph without picking your pencil up off the paper, then it's continuous. If you have to pick up your pencil off the paper, then it's not continuous. And then you just kind of move on. And then you get to Calc 3 and it's like, oh, we needed to know that? That stinks. You know, it's a kind of a short-sighted approach, not your fault, the nature of things. All right. Now, if I give you another example, and it's really going to be the same thing, except I'm going to fill in the circle. All right. So instead of it being a closed circle, open circle, I'm making a closed circle. Now, along a curve, there really is no such thing as a closed circle, because there's no need for that, right? Because it's just another point. And the point would be a smooth, or part of the graph, you know, a smooth component of the graph, right? So what I would say is here, and again, I'm trying to keep it general, you know, so vague. F of A does exist, right? There is a point there now, right? Now, if you want to plot a point there, that's fine. But, you know, here's a point. Boom. Good looking point. As good looking a point as any. The limit also exists because you're aiming for the same location as you come in from the left and as if you come in from the right, right? And the one thing that we would have to assume here, because me saying that they exist, yeah, they could exist but not be equal. They exist and are equal to one another in this case, based off the diagram that I drew. So I would have f of a being equal to the limit as x approaches a of f of x. So therefore, this function would be continuous. All right. Now, it's really just a question of, all right, continuous for what? For all values of x? Well, no, I mean, just based off of what I have here, this diagram, right? It's possible that, you know, if we extend out to the left, to the right, you know, maybe there's a vertical asymptote. Maybe there's it's part of a piecewise function where there's a jump. You know, there could be all sorts of other possibilities. But based off of what we see in these graphs, we're looking at continuous functions. All right. So now it's just a matter of saying, all right, well, now that I got that, how does that apply to vector valued functions? Oh, it's the same idea, right? In A and B, that was a nice little review of Calc 1, you know, like the whole lesson that you should have gotten. Maybe you did, but if you didn't, then there it is, you know. So in C, when it asks, is R of t continuous at x equals -3? Well, yeah, because the limit's approaching a vector and the function is approaching that same vector, right? So I would say yes. And, you know, just because my notes frame it as yes or no doesn't mean, again, like I said before, the test is going to frame it that way. So let's be a little bit more specific. Yes, because R of t is equal to the limit as t approaches -3 of R of t, and they exist. All right. It's important that the limit is an existing value, right? Because if it's an asymptote, you could say, okay, well, they're both going to infinity. I mean, you could look at it and say, technically, and this is, it's more like, it's not really technically, it's more like theoretically, but if you're approaching a vertical asymptote, then the limit is approaching some kind of infinity. And there is a school of thought that tells us that the function itself is approaching that same infinity, but that's beyond, you know, that's actually a different subject, right? So let me minimize, geez, just shrink. Sometimes I choose the more complicated word just because I think it sounds better, but it's just go with the simple. D, R of t plus 2 minus R of t. And so this is kind of building us towards the concept of a derivative, right? At least as it applies to vector value functions, right? So R of t plus 2, that's just straight up substitution. I'll just chuck this right below. Because we already know what R of t is. So this is really the crux of the whole thing. So R of t plus 2 would be telling me, I'm going to use my writing tool here because my handwriting is garbage now. It always was. Yeah, no, I agree. All right, so in my R function, and you know what I'll do is I'll write R of t right below it, because I know that that's equivalent to t comma t squared plus 1. All right, so what I'm doing is I'm replacing each of the t's with a t plus 2. All right. So I want to clean this up a little bit anyway, see where that gets me. So let's do that. So, and I'll write it as part D over here. So R of t plus 2 minus R of t. That's what we're looking for. We're going to subtract the two components. T plus 2 minus t is just a 2. And then the t squared, the t plus 2 squared plus 1, we're going to subtract from that t squared plus 1. So I'll write that intermediate step there, but we are going to distribute it out and clean it up. Change the color here. And then we just fix the spacing a little bit. All right. So we're going to have a cancellation of the 1s. So that's something, I guess. T squared plus 4t plus 4 minus t squared. Right. The 1 minus 1 went to 0, so we're not worried about that. And then the t squared negative t squared cancel out. And this gives us a result of t and then 4t plus 4. All right. So then it begs the question, all right, so we can do that, which is just increasing our t value by some arbitrary unit 2, right? So, well, arbitrary to us, somebody else decided on it, all right? So then that begs the question of like, okay, so wait a minute, what about like f of x plus h minus f of x all over h, you know, like the slope of the secant, which allowed us to use the limit definition of a derivative in order to compute derivatives, which led to all the shortcuts like the product, quotient, and chain rule. Will those all be in play? And, you know, it kind of seems logical that if it works for this, it should work for that kind of stuff too. All right. So and that's kind of where we're at this point.
Excuse me, Professor. Could you? Yeah, thank you. I just want to see that part.
Yeah, I was just cleaning it up a little bit. All right. So I'll just kind of chuck in a little example here. And I'll put a star on the next one because the next one is really just kind of tackling the same idea again as A, B, and C in number 3. I'll give you an opportunity to practice that one on your own. All right, so let's say you have R of T plus H, for example. You know, we use sometimes H, sometimes delta X. You know, you can use delta T if you want. Yeah, maybe we'll do that. Minus R of T all over delta T. All right. So in this case, I'll use the same function, given that RT is equal to, so I don't want to get into that big beefy trig function. I'll do it with the not so beefy. I don't know if anybody would call it that, but as it'll turn out, not so beefy T comma T squared plus 1 function. All right. So R of T plus delta T would be, let me just use a blue highlight. Oh, too thin. All right, so T plus delta T, comma, T plus delta T, the quantity squared, plus 1. And I'm just going to move this over because I cannot control the size of my handwriting as I go. So minus T, comma, so again it's vector, T squared plus 1. All over delta T. Writing big and then shrinking. Makes it easier. All right. So then, you know, it's still distributive property and all that good stuff and subtracting components. But we're looking at delta T, comma. So that's the first 2 components. Well, the first component in the 2 vectors. Try to be a little bit more precise with the words that come out of my mouth. All right, so T squared plus 2T delta T plus delta T squared plus 1 minus T squared minus 1. I'm distributing on the fly here. All right, some common or like terms that can be canceled out. Now, delta T would be some scalar value. You know, T is the variable. Delta T is the change from that variable. Bottom line is that gives me some license here to do what I'm about to do, which is to factor out a delta T, that common factor. Before I do that, I am going to clean it up first, though. So delta T and 2T delta T plus delta T squared over delta T. Now, just this next part, what I'm about to explain, it doesn't always get interpreted the way I want it to be interpreted. And so I'm going to try to be as precise as I can about it, because I want you to understand that shortcuts are okay as long as you understand why you're using a shortcut, right? So I'm going to factor out the delta t, right, on the top. When I pull that out, that's going to give me a 1 and then a 2t plus delta t. And that whole thing is over the delta t that was already there. All right. So once I do that, I can cancel out the delta t's. Right? Because it's just like algebra 1, college algebra. You're canceling out a GCF. There's nothing wrong with that. But it's okay for you to look at this and say, oh, I got a delta t in each term in my vector valued function. I can divide each of those terms by delta t on the bottom, right? As a shortcut, that's fine. Vector division is not really a thing the way a polynomial division is, right? Or just simple division. So we don't divide by vectors or matrices. We multiply by reciprocals or we multiply by inverses, right? So there is a conceptual component that kind of permeates throughout all of this. And I want you to understand that we don't think of it as division, even though the action that we're going to take is dividing. All right. So as long as you know that there's more to it than what you're seeing on paper, I think you're fine. And that being said, I meant to put the angular brackets here rather than the parentheses. All right. So we have 1, 2t plus delta t. All right. So that's great. So then the big question would be, and I'm sure it's on all of your minds, what would be the case if I were to find the limit as delta t approaches 0? Because the minute you recognize this as a variation of the difference quotient, aka the slope of the secant line, when dealing with two-dimensional function-related mathematics, you had to be thinking, all right, well, the next step back in Calc 1 was to find the limit as h approached 0 or delta x approached 0, right? So that's what we would do here in our next step. And in doing so, something magical happens, but not surprising, hopefully not surprising. Right? When you replace all your delta x's with 0, we get 1, 2t. All right. And so just going back to the original function, which we started off with here in the side example that I created, which, I'll take it as a typo. If I'm going to do this much work for a side example, it should make its way into the notes, right? If you were to take the derivative of each component of that original vector valued function, you would end up with 1 plus 2t. So that's extraordinarily good news, right? So that means that what we just discovered was that all of our old rules for calculus, well, we didn't discover that all of them, but we discovered that there's a pretty solid chance that what we know from Calc 1 related to ordinary function function related calculus, that it still is going to apply, at least in some way, to what we're doing with vector valued functions, which is good news, right? You may not look at it, it's definitely good news by saying, oh, well, yeah, this is great news, dude. That means I got to do all this calculus. I'm looking at it the other way by saying all that calculus that you studied, learning the product, the quotient, the chain rule, and then all the techniques of integration, they weren't for nothing, because we can actually apply that in the context of vector valued functions, which we already know transcends 2 dimensions. it's going to work in 3 dimensions, 4 dimensions, 5 dimensions. You know, so the calculus skills that we know already are going to be useful, right? So that's really good news, right? So yeah, what I'll do is I'll stop the video here and start a fresh new one because this is a pretty good place to break it up. Stop recording.